You know, there's this invisible force that pulls an apple from a tree, that keeps the moon locked in the sky, and holds entire galaxies together. Well, today we're going to dive deep into that incredible force that literally shapes worlds, gravitation. And that brings us to the big puzzle we're going to solve. Think about it. An apple on a tree lets go and it falls straight down. But the moon, which is also being pulled by the Earth, falls around it. They're both falling, so what's the deal? Why are their paths so completely different? To get to the bottom of this, we have to realize we're looking at a tale of two falls. It's true, the apple and the moon are both being pulled by Earth's gravity. Our mission here is to figure out the one single rule that explains both of their very different journeys. And here's the absolute key to the whole thing. We're not talking about two different kinds of physics here. It is the exact same force, the same universal principle that connects a tiny little apple to our massive moon. So let's go find out what that principle is. And for that, we have to thank the one and only Isaac Newton and his law of universal gravitation. This is it. This is the master key that's going to unlock this whole mystery for us. The law itself is it's beautiful, it's simple. It just says that everything with mass pulls on everything else that has mass. I mean, you have a gravitational pull. The screen you're watching this on has a pull. The Earth obviously has a massive pull. It's happening everywhere, all the time. And Newton broke it down into two really simple ideas. First, the more stuff, the more mass an object has, the stronger its pull. That's why we feel Earth's gravity, but we don't feel the pull of, say, a building next door. And second, the farther apart things are, the weaker that pull gets. Now, it never actually drops to zero, but it definitely fades with distance. So, okay, let's apply this to our apple and moon puzzle. The apple is super close, so the force is really strong and obvious. Boom, it falls straight down. The moon, on the other hand, is way, way out there, so the force is weaker. But get this, it's still powerful enough to hold the entire moon in its grip. Now, this explains the strength of the force, but we're still missing that key piece of the puzzle. Why does the moon move sideways? And this is where we get to the most brilliant insight of all. It is actually possible to fall without ever hitting the ground. It's this amazing concept of falling around the world. So yeah, the big question is, how on earth do you fall forever? The secret isn't about getting rid of gravity, not at all. It's about using it in a really, really clever way. Okay, I want you to picture this. Imagine you're standing on top of a super tall mountain. If you throw a cannonball, it travels for a bit, and then gravity pulls it back down to Earth. Simple enough. Now throw it faster. It goes a lot further before it finally hits the ground. But what if you could throw it so ridiculously fast that as it falls down, the Earth's surface curves away from it at the exact same rate? Well, then you have it. The cannonball is now constantly falling, but it never actually gets any closer to the ground. It's in orbit. And there it is. That's our answer. An orbit is nothing more than a state of continuous free fall. The moon is always falling toward the Earth, but it has so much sideways momentum, so much speed, that it just keeps missing. The apple? Well, it has zero sideways speed, so it has nowhere to go but straight down. Now, this whole idea of being in a constant state of free fall, well, it has some pretty mind-bending consequences, especially if you're an astronaut. You hear it all the time, right? Astronauts in space are in zero gravity. Well, I'm here to tell you that is a complete myth. At the altitude of the International Space Station, Earth's gravity is still about 90% as strong as it is right here on the surface, so it's nowhere close to zero. What they're really experiencing is constant free fall. This quote just nails it. The reason astronauts float isn't because there's no gravity. It's because they, and the space station, and every single thing inside it are all falling around the Earth together at the exact same speed. It's kind of like being in an elevator when the cable snaps. For that terrifying moment, you'd feel weightless because you and the elevator are falling together. Astronauts are just stuck in that moment forever. So orbiting is all about going just fast enough to miss the Earth as you fall. But what if you wanted to go even faster? I mean, what would it take to just beat gravity completely and never fall back at all? That speed has a name. It's called escape velocity. And for Earth, that is a mind-boggling 11.2 kilometers per second. That's almost 25,000 miles per hour. If you can get an object moving that fast, you will break free from Earth's gravitational pull for good. You're not coming back.
So, you see, gravity is this cosmic glue. It's the force that allows for planets and stars and even life as we know it to exist. And we've learned how to dance with it, to create orbits, and even how to overpower it to explore our solar system. Which really leaves you with one final thought. Gravity holds our entire world together, so what happens to us when we finally learn how to break free from it for good?